Hello and good afternoon, everyone. Super excited to be here today, and I'm actually going to start right away by showing you this image as an illustrative example. Well, you might ask yourself, what is this entangled and rather messy-looking structure? And to not keep you waiting, this is an illustration of our dependency graph for the mobile code base at Spotify. In total, we have over 33,000 different build targets and over 70,000 internal dependencies between these different code entities. What you see in the bottom left corner is a simplified view of this build graph only for our Android project. Here, the nodes in the dependency graph are represented by the small circles, and the arrows that you might be able to distinguish are the dependencies between those. Even though this is a simplified view of our graph, you might recognize that this poses some interesting problems. Because of the vast size and the high number of dependencies and targets, it becomes hard to reason and understand how this graph looks like. This is especially true because of the transitive nature about how things are implicitly related to each other. If we take a step back and look at the mobile code base at Spotify, it has been growing a lot. Over the last few years, we have had a steady growth of about 30% year over year. And this has led to a drastic increase in the raw number of lines of code, and the workloads to interact, build, and test our code has grown heavier and heavier. At the same time, the dependency structure that I just showed you have also become more and more complex, basically leading to a deeper and more nested structure. And these two things together has led to gradually slower build times, both locally and in CI. And in order to counteract this, we have highlighted the need for working on architecture improvements in order to work on the structure of our dependency graph and thereby bring speed to our mobile developers. As the dependency graph keeps growing, one example of this increasingly nested structure is illustrated by this chart. This is for our iOS project and is showing a top list for one of our metrics that describes the number of invalidations caused in the graph by code changes to a specific build target. Here, iOS pill in the very top stands out much more than the rest. And this is a fake name for one of our targets, but to give you some more context, it is a common UI design system module that basically has grown to contain a whole lot of our reusable UI building blocks that we use throughout our applications. Because of its nested position in the graph, the vast size and the frequent code changes to it, it causes cache invalidations that not only slow down the people directly interacting with it, but also everyone else who is transitively depending on it. And with this short introduction, I want to welcome you to our talk today about driving architectural improvements with dependency metrics. My name is Carl, I'm a data scientist at Spotify, and I'm joined by my colleague John today, who apparently chose almost the same outfit. And we will talk about our journey at Spotify and how we've been creating and leveraging dependency metrics in order to understand our code base and our dependency graph in spite of its vast size and complicated structure. This has been used in order to prioritize our engineering efforts to make the most impact with our engineering work. So, to give some more context about who we are, we come from a part of Spotify called Client Platform, which is the organization that is responsible for the underlying architecture, the tooling, and the developer experience for our client developers. Me and John are part of an insights team of data scientists, data engineers, and user researchers who support our client developers with how we can use data and insights from our development environments, our build systems like Bazel, in order to understand our products better and being able to take better and more strategic decisions. Before diving into what these dependency metrics that I mentioned actually are, I want to pick up from the example in the beginning and talk about the need for isolating our code base. So, as I said, we have seen a rapid growth of our code base, and this has created a deep and nested structure where certain pieces of the code act as bottlenecks that basically cascade issues and invalidations so that they affect many others. By breaking up these bottlenecks, however, we are working on trying to make this structure more flat and wide in order so that we can take better advantage of parallelization of the build processes and Bazel as a build tool. And this also makes it possible for us to reduce the cognitive load for our developers as they are working with the code base. And thanks to this effort of isolating the code, as well as moving over to Bazel as a build system, we have been able to bend this increasing CI build times curve that I showed you in the beginning, and we're now seeing gradually improvements day by day. So, to illustrate some of these concepts about bottlenecking in our dependency graph, let us first consider what could be a good platform library. In this case, illustrated by the pink circle, we have a library that has a small and stable API surface. And then we have all the explicit downstream dependencies on the right, meaning the consumers of this API. In this case, because of the stable API, any changes that happens to the implementation logic of our library will not affect any of the downstream dependencies. However, if we have a bad API design, where our pink target here rather brings in a whole lot of upstream dependencies to it, any changes that might happen on this left-hand side will also invalidate our pink target and thereby cascade and affect our downstream dependencies on the right. Another example of a bad platform library are these type of thick and fat APIs, and this is illustrated by the thick, fat, pink circle that we see on the screen. Here, we haven't properly separated out the implementation from the API logic, and all of this is contained in the same big target. Because of the vast size, it becomes heavier to build and process, and also, since the implementation logic are contained directly in it, we see a lot of changes directly to it, which then invalidate it and then causes issues also to the downstream dependencies. And the iOS pill that you saw in the beginning in the top list is one example that behaves something like this. So, as a way to understand these type of phenomena of bottlenecking in our dependency graph and identify them so that we can improve and counteract them, entering now graph analysis and dependency metrics as our proposed solution. And as you've seen so far, the dependency structure between build targets can be represented by this mathematical graph or a network, something that could look something like this. And this type of network structures is very common across research and engineering in general. For example, if you're modeling social networks, if you're looking at the spread of diseases and epidemics, etc. And over the last 50 years or so, this has grown into an old research field with a whole lot of methods and tools in order to understand this structure and what are the certain pieces of it that are most important. And our dependency metrics that we will be speaking about today is an application, an extension of these type of graph analysis tools into the realm of software development so that you can make sense of it and draw conclusions for our dependency graph. So in a nutshell, we have created this type of enriched dependency metrics. And you can think of them as basically being built by two main aspects. On the left-hand side, we have the structural properties of the graph. And for this, we use Basal Query as a tool in order to extract information about our build targets and how they are related to each other. We can then build up this mathematical graph that we can then analyze with graph analysis tools. However, what we've also added is a behavior layer to this. And this is perhaps a bit less standard when it comes to this type of graph analysis. And instead, we look at how our developers interact with the code. And the reason why this is interesting is that having a nested and complicated dependency structure is not necessarily a bad thing as long as things remain stable and don't change often. However, if we have high code churn in certain parts of the graph, this can be cascaded through those nested dependencies and thereby cause issues in the graph. So it's this combination between the behavioral aspect and the structural aspects that then captures some of these ideas that we want to understand and use in order to drive improvements to our code base. And to give some examples what this could look like, on the structural side, we have information such as the raw shape of the graph, if it is deep or if it is flat and wide, as well as centrality measures that describe how certain pieces are important because of its relationship to others. On the other side, we have the behavioral aspects where we use GitHub data about pull requests and how people are interacting with the code. We then attribute this to our dependency graph so that we can build up bottleneck scores that describe this type of cascading and transitive nature or issues in the graph. So, with that basic terminology defined, let us now try to illustrate this so we get a better feeling about what these type of metrics are and how we can use them in practice. So let us consider a single build target A, represented by this little circle on the screen. We can then expand it to also show our explicit downstream dependencies, just as you saw before. Notice here the direction of the arrows, pointing from our build target to the downstream dependencies on the right. However, in reality, there might be other pieces of code that also depend on these rightmost targets, and by traversing the graph, we can form the full transitive tree of downstream dependencies. And just the number of such transitive dependencies are interesting because it shows how many other build targets are affected by changes to A. As another structural property which have been very useful for Spotify is to think about this in terms of depth. And the way that we do this is by computing the longest dependency chain starting from A and that passes through the downstream dependency graph. In this case, we have a depth of 5. And we have used this in order to guide our efforts and understand improvements in how we manage to flatten out this dependency graph and make it wider rather than deep. So if we now bring in the behavioral aspects that I talked about before, we look at the pull request from GitHub and can then, thanks to Bazel query and the natural way of mapping source files into our dependency graph, we can then attribute how often over some sort of time window this has been changing. And for this, we then define a metric called rebuild targets, which tries to capture this. In this case, we sum up all the changes to our build target A, and we then multiply this by the total number of transitive dependencies on the right. And this can be interpreted as a score for how those changes basically impact the other targets in the graph. However, in reality, though, A might have this whole other upstream tree on the left. And if we then expand it, in reality, any changes that happen to the pink targets on the screen now will also cause an invalidation and thereby be cascaded through A. So therefore, we define a related metric, which is called rebuild targets by transitive dependencies. And this is basically we then sum up all the changes on the left-hand side and then multiply it by the number of transitive downstream dependencies on the right. And this is an interesting one because this can act as a score for bottlenecking or bottleneckness in our graph, because we can interpret this as how much a single target, like the one in the middle here, acts as a force multiplier for these type of cache invalidations through our graph. And by having this, we can use that to identify certain pieces of the code, but if we can split it up and isolate it, we can basically have large positive impact on the way that our graph looks like. A related such score is something called betweenness, which you might recognize from the field of graph analysis if you're familiar. And this is basically the fraction of all dependency chains that passes through a single target. So this can also help to identify where are those sort of culprits in the middle that if we can cut them out and isolate them, we can have large positive impact. So let us now click through and consider a single build target A in this case. And what would happen if we would now sort of properly or optimally isolate this? In this case, we could split it up into an implementation and an API target, similar to this. In this case, the implementation logic is within the impl, and that also contains all the upstream dependencies to the left. Here, any changes that now happen on the left-hand side will flow down to the implementation target, but since we implement a stable API, this will not affect the consumers on the right-hand side, which then makes it possible to drastically flatten this out and make it much more, less invalidations in the graph, and that we can parallelize it better. So in total, what we've seen so far is that we do this for a single target. For example, this target A that we saw in the middle. But in practice, we run this across all our entire dependency graph, and we do this every day in order to compute these structural properties. And we can then use this in order to understand when we see structural improvements and also to guide where we should focus our efforts and try to break up these type of things. And I will now hand this over to John, who will talk about and demo some of our dashboards and how we can use this in practice.
Right, thank you, Carl. So now I'd like to go into demo mode, and I'd like to show the dashboard and the tooling that we built and used internally to track and follow up on the dependency graph and its metric throughout the company in our Bazel journey. So let's jump straight in. So this is the main overview of the dashboard that we've been building. And as you can see, it contains a bunch of different views and different information. And we built it this detailed on purpose because we want to enable developers to really do a deep dive and learn about the dependency graph so they can identify issues and find bottlenecks, and that has an opportunity to be refactored and improved. So I'd like to go through some of the things you can do with it and some things we've used it for. So in this top view that we highlight here, as Carl mentioned, we have tens of thousands of build targets in our dependency graphs. So it can be quite hard to find the most important one and know where to look. So that's why we created this view where we sort all the build targets based on the currently selected metric. In this case, is the rebuild target by transitive dependencies, as Carl explained previously. You can also see that there are different colors of the bars. Blue is for our shared C++ core libraries, orange is for iOS, and green is for Android. We also have a range of different toggles and filters in the dashboard, allowing you to slice and dice in whatever dimension you're interested in looking at. And by updating this highlighted one, the top list metric, we change what metric we are sorting the build targets on in the top list. So let's try updating it, and instead look at another metric mentioned by Carl, the betweenness over the longest dependency chains. And as we can see, the list of targets updates, and we're now looking at only C++ core targets. But for the purpose of this demo, I'd like to show some Android targets instead. So I can simply go into this client filter, select Android, and the targets we're now seeing is only coming from Android, and all the build targets are reflecting that. So looking at this top list, we can see that there are 2 targets standing out. And maybe we'd like to learn more about how and why they are standing out, so we can select one of these targets and do a deep dive. So in this case, I'd like to look at this made-up name called Android Quest. So I'd simply press the green bar and go into a selected mode, where some additional information is available. So the first thing I can do is that I can hover over the selected bar to get a time series plot of how the metric has changed over the last year for this build target. And we can see here how the between score had stayed pretty stable throughout the year, but then dropped in the beginning of October due to some recent refactorings. In this bottom view, we show the value for the build target across all the available metrics that we have in this dashboard. Side by side to that, we show the average value across all build targets. And side to that, we show the distribution plot across all the targets for the given metric. As an example, in the top row for the downstream dependency depth, Android Quest has a dependency depth of 18. The average score across all the build targets is 4.3. And that is also reflected in the distribution plot, where you see that most build targets have a depth lower than Android Quest, and thus are placed on the left in the distribution plot. Let's see. In the same view, similar to above, you can hover over the build target and the metric for that row to get a time series plot of how the target and metric has changed over time. All right, let's move on and look at some other things that we've been using this dashboard for. I'd like to go back and stay on Android, but look at rebuild target by transitive dependencies again. And we have been relying on this metric a lot internally when we've been driving improvements to the dependency graph. And we have used the metric to find potential high-impact candidates of build targets that we like to refactor and or improve the dependency structure of. One thing that we tried to do was that we set a cap on 10,000. And then we looked at all build targets that scored higher than that for the rebuild target and selected them as candidates to sort of take an additional look at and try to restructure. I'll come back to the outcome of this effort just after the demo. Let's stay on rebuild targets by transitive dependencies, but look on iOS instead. By looking at the top list here, you may remember the topmost one from the presentation by Carl, iOS PIL, the common UI design system target that has historically been a large dependency graph invalidator for us. And in this view, you can notice the score that the target has a score around 24,000. But going back to the example from the beginning, you can see that the score was drastically higher in that image at 146,000. But this was back in April. And during the last months, we have focused specifically on this target, refactoring and splitting up the build targets into more granular ones. And if you look at the same time series chart again, and please ignore the data before the 1st of May, because that was when we started calculating the metric properly, you can see that we've been able to consistently bring down the score over the last quarters, leading to much fewer cache invalidations happening throughout the graph. And this metric, and the dashboard in particular, has been really useful since it has allowed us to see, but also communicate and celebrate all the small step-by-step improvements that we make along the way in this gigantic effort of splitting up this big target. Another view I'd like to show, still staying on the iOS targets, and you can focus on the top one here, is how you can inspect the distribution of build targets on the different dependency depths. So in this view, you see on what depths most build targets are. And you can see that we have 2 significant peaks in the graph, and that is quite deep and not as wide as we would like to have it. But again, this particular snapshot is from the beginning of the year. And this is something that we've also been focusing on a lot, trying to squeeze the graph together and make it flat and as wide as possible. So looking at the current date, you can see that we made significant improvements in reshaping our dependency graph and flattening it, allowing us to better utilize the parallelization capabilities that Bazel gives us. In this final view of the demo, we are looking at Android once again and a recent architectural regression that we saw. In this view, you can look at the average value for the rebuild targets across all the build targets in our graph. And if you look at the arrows where the arrow is pointing, you can see that the number drastically started increasing in early September. There were some recent architectural changes as part of building a new feature that caused these cache invalidations to increase. But with the help of the dashboard, we could quickly communicate with the team, telling them about the impact that their change had, and they could quickly come up with an alternative dependency declaration that prevented and mitigated the issue and prevented a lot of cache invalidations to happen. That was it for the demo, and now I'd like to move on and highlight some of the success stories we've had in using these metrics internally over the last year. One of the key opportunities in having metrics and a dashboard set up like this is the ability to communicate and celebrate around the architectural and structural improvements work we are doing throughout the graph. One such example you can see in the image here, where we were able to use storytelling in a Slack message to explain how and why a single, quite small PR could impact the entire dependency depth of the graph, bringing it down from 34 to 27, and why it's important to keep the graph flat as well. This kind of communication is useful because we can promote and educate and align the organization on the work that is being done and the impact it is having for everyone across the board. Looking back again at the example of iOS Pill in our iOS project, where we made drastic improvements over the year to the rebuild target score, we could see a more than 10x improvements in build times whenever Pill or related targets were changed compared to before, which is a huge impact in terms of build times. And as I mentioned during the demo, on Android, we tried to set a hard cap on 10,000 and took an extra look at the target scoring above that. After we made an effort to refactor and improve the dependency structure of these targets, we could see that we could avoid, on average, 66% of all the Bazel actions compared to before when any of these targets were changed. Again, this is also contributing a lot to build times across the entire project. Now, let's briefly touch upon the instrumentation setup and how we are collecting this and surfacing it. So we set up the instrumentation process into a handful of sequential steps. Internally, we have it packaged as a CLI tool that we run locally and in CI. We start by simply running a Bazel query, dumping the entire graph into the XML format. We then traverse all of the rule inputs and outputs tags in the XML to construct the complete graph. With the complete graph on hand, we have a decoration step where we add some additional metadata to the graph, such as internal ownership data and Git contribution data, marking all source files by the number of times they've changed over the last 4 weeks. But the complete graph we get from the XML file is really big, and it contains all the source files, file groups, and other targets. So to make it easier to understand and calculate the metrics, we have a condensation step where we allow the developer to specify what targets to keep and which ones to remove. And as we remove targets, we rewire the edges to keep the same connective properties of the graph and propagate the decoration data forward. Let's see. With this condensed graph, we then feed the graph into a metric calculation step using the Python library called NetworkX, which allows us to do a bunch of different graph calculations on top. And we then output these metrics to the user. And here's an example invocation on the command line where we are calculating the upstream dependency depth. So we query Bazel, and after that, we are constructing the graph, decorating it with Git data, collapsing it, computing the metrics, and here outputting a top list of the dependency depth for the given project. So internally at Spotify, we use this dashboard to monitor and understand how the graph is changing over time. but also for setting targets and during planning, as we, for example, did with the Android target scoring higher than 10,000 and having this as a special effort. Also for visualization and exploring the graph and learning about the structure and communicating around the work and impact it is having. We also recently started calculating this metric on every PR, allowing us to know which PR introduced a particular regression to the graph, giving us the information at the right time. And we're just rolling out the ability for developers to run the tool locally as well, so they can more interactively explore and tweak with the dependency setup of the project and see if the changes they're making are having the impact that they expect. Finally, I'd like to look at some learnings and next steps. So these architectural regressions, they tend to happen over time as the project grows. But as I talked about just recently, we saw this recent architectural regression on Android in early September, but also how we started to calculate this metric on every PR. So one thing we're talking about is potentially making it even closer to developers, potentially by introducing some kind of check in the pull request workflow, where we can notify the developer that, hey, the change you're making is having a big impact on the dependency structure. Are you sure you would like to go ahead, or can you think of an alternative dependency declaration? We're also looking into further decorating the graph. For example, internally, we also capture the build event data for all local and CI builds. It would be interesting to see if we could also utilize this data to draw additional conclusions about potential issues and bottlenecks in the graph. At the same time, we also collect cache statistics and basal diff and avoidance data that we could also use to learn about issues and about the impact of the work that we are doing. And finally, so far, we've been using this as an internal tool. We see this also as an opportunity for the Bazel ecosystem by possibly integrating this into a tool like Bazel Query itself, allowing everyone that is using Bazel to use tools like this to understand more about the dependency structure and the graph of their own projects. So for more discussion on the next steps for these performance and dependency metrics in the Bazel ecosystem, we will host a Birds of a Feather discussion tomorrow, together with some engineers from the Google Bazel team. So hope to see you there, and thank you a lot for attending the talk today.